Before I start, I would like to acknowledge the contribution of your Honorable Chief Minister, Somanath ji, for making this event happen continuously in the last 5 years, and this year in much better scale, and also identifying a young scientist for this award. So all congratulations to the Chief Minister and his government for making this celebration of Manohar Parrikar Vidnyan Mahotsav for the benefit of the young talents of this state. Thank you so much for having me here. This is a great opportunity to interact with the community, especially students in Goa, to speak about first on the accomplishment that Isro has. It's really last 60 years we have achieved substantially in terms of satellite building, launcher building, application delivery, science and technology development, capacity development in the scientific fronts in various domains. I think many of you may know that space technology is just not a elite technology of anything like that. It is conventional science and technology domains where there are many elements come together to create something like rockets, spacecrafts, and applications. But then it's a very complex one. It is not a domain where you can easily get through with mistakes, because always you would have watched the failures that we encountered. So having success in space missions of this nature, because the final mission is always acted only once, never practiced before in reality. That's why it is very beautiful, and that's why it's challenging, and that's why there is an excitement in each one of us to continue work on it. So in the last so many years, we were able to develop rockets, spacecrafts, and launch it from Indian soil. I think all of you know that India, having achieved this, is not a small feat for a nation like us. When we started the whole program, there were criticisms, like the Atomic Energy Department itself, when Sarabhai and Homi Bhabha started it. All criticisms were overcome today. I think we are very proud of the accomplishment. So I won't spend more time on it. But today we are considered as one of the important launching nations of the world, where private people are willing to come and then get their satellites launched. Recently we launched 72 satellites for one web company. It's a great achievement using our LVM rocket. The launcher technology development evolution over a long periods of time has been one of the hallmark of our capability development. Specifically because building rockets and launching has never been an easy task. If you really count the people who have an ability to build rockets and launch it, there are not many people in the world. You know that, no? You can count it as US as a nation. Europe had a problem and now they are struggling to get through the difficulties. Russia, China, Japan. And that's it. I think there were no other nations could come up with this capability. Of course, there are attempts and efforts all over, primarily because of the huge investment which are required in this and the risk associated with developing it. But if you really look at our story of building rockets from the SLV-3 days when Kalam built those rockets to what we have built, the LVM-3 rocket in 2019, I think it's a great story of having indigenous capability to build rockets in India and then launch them successfully. And this didn't come by accident. It came by very calculated, planned strategies encountered in creating technology capability. Building solid boosters, solid motors of very large scale. And we are some of the third largest ever solid motors we built. Liquid engines. We actually got this technology from Russia, France, etc. to start with. Of course, Russia did not give us any technology. We got the engines and we developed it next 20 years, struggling on cryogenic technology. And we are now working on futuristic engines like Slox Median ourselves without seeking any technology from anybody. These engines were very, very important. Liquid engines, solid engines. I think when you look at these engines, you must also know a very important aspect. Today in India, look at the aircraft engines. No, hundreds and hundreds of them we use in aircrafts. Still not manufactured in India. We have only the Kaveri engine is still to go through many troubles and qualification processes. But we have rocket engines manufactured and tested and flying successfully in India. I'll just compare the engines of aircraft to rockets. Typically the rocket liquid engine, which is a cryogenic engine used in GSLV Mark III, C25 engine we call it. The power of that is almost 35 megawatt. You just compare the aircraft engine, it's only a few megawatt. So highly intense, power-dense designs with materials, technologies, heat transfers, and complex turbo machinery all input in once for just hardly 1,000 seconds, and then gets into the sea. Even then, such a complex machine, we were able to design, realize using in industry and manufacture, test and fly. It's not a small task. Of course, the whole of this space technology came out of the research and development capability that we have created within the organization, the Isro. The propulsion technology, both for rockets and satellites. Of course, the understanding of aerodynamics. I think I go back to on my days when I joined Isro. It has been a topic of great discussion in all our meetings. Understanding aerodynamics is not so easy at all. It came from the academics, the academic places. Science, it is technology, Kharagpur, Mumbai, Delhi. All of them contributed to professors from those universities, came forward, discussed with our scientists and engineers, and created this capability today within the organization to understand aerodynamics, flying through air, and how these loads and controls affect them. Electronics has been very crucial for safety of the systems. Sensors of various nature, optical, inertial, structures, composites, pyros and chemicals. Even chemical technology is so crucial for rocket building, the propellants. How they are realized, how to generate energy out of these propellants, the structural characteristics, processing nature, then huge ground infrastructure for communication, networking, and connection which are required. Even for Chandrayaan, I will tell you how much complex is the network communication infrastructure even to make that mission succeed. So huge amount of technologies, capabilities that we have to develop over long periods of time to do all of this. And we continue to work on key technology areas. I think this is something which all of you young people must be aware. Everybody need not design rockets and satellites. You can work on key domains of technology. For example, material science is so important for us. And one example I'll tell you, for a typical cryogenic engine, we need 50 different metallic materials. And all of them are complex alloys. And all these alloys, when we started building it, all came from Russia. Today, all of them are built in India because we have metallurgists, material processing engineers who are able to convert these imported alloys to an Indian equivalent alloy and produce in India to the quality required for space. It's a great achievement. And it didn't come from Isro alone. It came from various institutions in this country who contributed on the metallurgy of metallic materials. It's same for non-metallic materials, composites, adhesives, chemicals. You get paints, ceramics, glasses. There are magnetic materials. And each of them you have huge amount of research opportunity. And new approaches in material science is coming in terms of additive manufacturing. Have you heard of additive manufacturing? I think many of you would have already heard about additive manufacturing. And how this can be used in space is a very important topic we are discussing. Of course, there are conventional designs for aerodynamics, propulsion, rockets, satellites, air-breathing engines, space missions as Maharaj does in trajectory designs, how to travel from Earth to Moon or Moon to Mars. I think all of these are complex mathematical calculations that are involved. I think all of these are part of our knowledge building, design capability development over the last so many years. And the pinnacle of all of this is going to be the human spaceflight program. When we send our Indian to space one day through the Gaganyaan program, I think the amount of skill that you need to have, the confidence we need to have is going to be one order higher than what we are currently having. And that confidence building process is something happening all across Isro today with the support of national laboratories. So many laboratories are participating in this. The first part is, rockets are always bound to fail, we say. Whenever it is ready for launch, our tension and heartbeat goes up because though even if the rocket is built very, very safely, having all the processes followed, everything is good, something can still go wrong. And if it goes wrong, there is nobody able to go there and correct it, adjust it, modify it to make a successful launch. It has to happen. Thousands of elements should work without any flow to make a launch happen. So we have always the risk of failure. So when you have a failure possibility, at least statistically, then we must have protection against it in a human space flight. And this is a core of the human spaceflight activity, that we should not put the risk of having the astronaut lost due to a failure in the rocket. So it calls for intelligence in the rocket now. So this is what we are working today. I think for the people who are in the new generation understand what is intelligence is and how to create intelligence in machinery by sensors, data processing, artificial intelligence to create synthesis signals of various nature and then come to a conclusion that the rocket is going to fly safely or it's going to fail. And that has to be decided in less than a fraction of a second. And then you must tell the rocket, it's going to fail now, you better abort. even before the failure occurred. So this is a challenge of working on the intelligence in a rocket, and we are working on such technologies today, looking at the data which is available in measurements, and then make a synthesis of it and understand whether it will fail or not. And there are so many new technologies we are developing, especially to handle human spaceflight, like handling the living conditions of an astronaut within a crew module, for example. You know, when you are here, you have air, oxygen, your waste disposal, everything happens. But when you are in a confined environment, everything needs to be taken care. Your temperature must be controlled. If it goes up by 5 degrees, you become exhausted. Your percentage of humidity has to be there. Fire safety has to be there. So we call it environmental control and life support system. And we have no experience of doing it till now. We were only designing rockets and satellites. And we thought that this knowledge will come from some other nation. But unfortunately, after so much of discussion, nobody is willing to give it to us. And we decided that we will do it ourselves. And we are in the engineering model level today for the Gaganyaan program. And we are going to develop it in India using the knowledge we have, using the industries that we have. The environmental control and life support system for Gaganyaan program. So we started the program with the last launch. Probably you would have seen the test vehicle launch, where we sent the crew module up there, aborted, and recovered it back in the sea using parachutes. And that mission particularly, which you would have watched, some of you would have watched, right? Yeah. Anybody watched that launch? Gaganyaan test vehicle D1, the last launch. Anyway, I will show you some slides on that. You will understand that it's such a complex mission, having so many systems working in very short periods of time in a very sequential manner for the parachutes to come out successfully and then make the landing with a precise velocity. Otherwise, if you hit the ground with a velocity of more than 10 meters per second, you will die. All the astronauts in the whole capsule will die because the deceleration level anybody can handle are almost reaching the threshold. We also developed, while we were working on all of this, we developed a rocket called SSLV. This is another interesting story which I want to tell you. Because we want to develop rockets which are very low cost. Low cost means really low cost. I will not disclose you the cost because somebody will understand that it is so cheap. So we want industries in India to build rockets and launch. It's not Isro alone should build. We wanted to build this rocket, prove it, and hand it out to industry so that they can manufacture it, operate it at technology levels which are one order lower. I won't say one order, maybe a little lower than the current knowledge, so that it is cost effective for putting certain applications and satellites in orbit. Small satellites are becoming very, very popular. I think all of you would have seen. So many universities are developing mini satellites, small satellites, and everybody wants launch opportunity. So we developed this. We had a very successful launch this year beginning. We are also developing reusable winged rocket. I believe that you would have seen some videos of Isro where you would have seen an aircraft-like craft coming and landing at extremely high speeds after dropping from a helicopter. We had a helicopter flight of this, took it almost 4 kilometers up, released it, and it autonomously landed. Maybe Madhuraj will be speaking something about autonomous landing of such crafts and how you achieve this using sensor fusion. So this is an important element of our development. Still, we want to continue to develop winged aircraft-like objects, which will go to space and stay in space for months together, do some activity like science or experiments or surveillance, and after a few months, it will come back and land on Earth, and we can recover instruments, recover samples, again launch it using like a space shuttle thing, but it's not a manned craft. So we are developing such technologies also concurrently. So today, when we look at our number of satellites in space, India has almost 50 plus satellites in space. They are communication satellites, they are Earth observation satellites. Earth observation means remote sensing, we call them. Then we have navigation satellites, and we have science missions, which are already there. So almost 50 satellites we are currently operating, and this requires operational maintenance, data collection, commanding, maintenance of any anomaly. All of these are involved while we have an operational satellite system. So this is the type of distribution, and this includes strategic satellites also. You may wonder that we launch satellites to observe our borders, and our security of the nation depends on many of these observations today. And we also have our navigation satellites, which is very important to look at, to provide you services like the GPS equivalent services, specifically for the strategic users. So if you look at far away, like 1 lakh kilometer away from Earth, and look at Earth, you will see like this. All Indian satellites are all above India in the equator, moving around, which includes the satellites which are there for communication, navigation, all of them distributed from one east to west along the equator, providing you communication services for civilian use as well as special users. So this is something which we call our orbital slots, and this is a very precious resource for us. And these are just not available to any nation just like that. Possibly you will understand what's the importance of orbital slots, acquisition of orbital slots, maintenance of them, frequency management. These are all very critical national assets and resources. So we have captured it from the global demand and then put our satellites there and operating for all your needs. You know, your television broadcasting today, DTH services are all through the satellites. Your ATM services, we call them through small aperture terminals, we communicate through satellites and then send the signal back and forth when you transact your money. We also give disaster warning support using the satellites. We do financial transactions for banks across various sectors, and many other communication services which are backhaul of our mobile, even network communications are all happening through the satellites. So all of these are very important national assets to maintain the communication services. And equally important is the NAVIC service, which is nothing but the timing and position service. You know GPS, many of you know GPS, right? And you know GPS is a global constellation which provides you position and timing services, and it's there near all your mobiles. And you can use your Google Maps and GPS integrated for you to travel. Same thing can be done using this, but unfortunately it does not become available in mobile yet. It is currently available only to strategic users with the secured codes and special things. Civilian has already come in some mobiles, around 30-40 mobiles we have NAVIC, but it is going to come to every common mobile now because of the frequency. There were some issues in the past. We were not getting the more friendly frequency called L1 and L2. Those were some idea about the frequencies you will understand. NAVIC operate in L5 and S band, whereas the GPS operate mostly in L1 and L2 band. And we are trying to bring those bands in our NAVIC so that it becomes very popular. In remote sensing, we have huge number of satellites, as I already showed. They call it Earth observation satellites. And this is something called domain special satellites. For example, if you want to look at land and water, you need one type of satellite. If you want to look at very high resolution, you need another type of satellite. If you want to look at ocean, then you need another third satellite. Weather and climate, yet another type of satellites. And each one of them look at the same scene with different frequencies. No? You know, you are able to see light in the visible spectrum. But when you look at Earth, there is radiation in all spectra. And you can see in thermal, near infrared, ultraviolet, and further wider. And when you look at in all these bands, you can get various information. Temperature measurements, humidity, the density of water vapor in that, the aerosol content, the pollution, the surface nature of that sea, the surface temperature, the color of the sea, and then find out the wave heights. You can also use radars to find out altitude variations. You can get stereo images, and you can also get the cyclones formation genesis and its making prediction. There are a lot of such things possible using remote sensing, and all these remote sensing satellites are designed and built by our own scientists using our own technology. And this is something very, very unique, which includes making very complex camera systems, optics, detectors, processing electronics, and so on and so forth. And we also did various collaborative work with other nations as well in this sector. And we continue to build large number of remote sensing satellites for supporting the nation. And most of the remote sensing data products are available through Bhuvan. I think I request young people to at least type Bhuvan in your app somewhere and then try to see the India-specific remote sensing data outcome. Please do it. Without forgetting, please do this. You go to Bhuvan, you can go to India, any state, and get huge amount of information which is generated using satellite data. And there are a lot of applications. Look at water, earth, the desertification, the rivers, the flooding, which is happening today. If there is a flood happens somewhere, but the prediction of the flood is always available, and so much information is available in Bhuvan. Please don't forget to look at it, because it's a free service for most of you, but there is a paid service also for very higher level of data. Now let me look at some of the talks which you all are excited about the lunar exploration. I think all of you have seen the Chandrayaan-3 landing?
Yes.
Yes. Live? Or post-launch, post-landing? Okay, I think I'm sure there was a great excitement on the day of the landing, including me, of course. And we were very tense into the fact that all of you are watching, not otherwise that there is anything going to happen. Because we want to make sure it is going to be a success for all of you. And it turned out to be so. And it's not a magic, it happened by the work of a generation of people working on Chandrayaan 3. I must acknowledge that. It started with the Chandrayaan 1, and then Chandrayaan 2 and Chandrayaan 3. And I always tell people that it is because Chandrayaan 2 had a problem that we had success in Chandrayaan 3. It's always like that. In space missions, a failure gives you so much of information that a success will not give you. Because it brings out the problem and weaknesses in any design, and that you can correct always. So the Chandrayaan 1 was a launch where we had sent the satellite, not for landing, it's just to become an orbit around the moon and do some remote sensing experiment, like the remote sensing Earth observation satellite with instruments on board. And this Chandrayaan did fantastic thing. You know, Chandrayaan 1 is the satellite which found out what presence of water on the moon. Ever since 1960s, people were going to moon, but now none of them could actually identify. Because there were two instruments, one from US and one from India, which had specific capability to look at the hydroxyl molecules. They identified it, and later it could be corroborated by further observations in Chandrayaan 2 and other moon missions to guarantee that the observation is correct. And we have a full map of the water presence on the moon today. And Chandrayaan 2, of course, was a mission for landing on the moon. Everything went very well until the last phase of the soft landing, where something went wrong. I will tell you what went wrong, just for your quick understanding, and how we corrected it to make the Chandrayaan 3 a success. I think this is something which is very exciting for each one of you. But before I go further, I would like to tell you Chandrayaan 1 was very, very exciting mission in terms of science and technology. Observation. For example, I just marked here the spectrum of the radiation, where it actually travels from the radio waves to gamma ray spectrum, where the visible spectrum is very small. What you are seeing, the natural light. But they are not visible to each human eye. But still you can make observations in all these spectra using appropriate instruments. So the Chandrayaan 1 was one mission in which we had instruments to look from one end of the radio spectrum to up to the gamma ray and various bands. So it actually brings out so much information about the object to which you are looking at. And this was possible because we had an international collaboration of bringing instruments from Europe, America and India in Chandrayaan 1. And this was a fantastic mission because of that. We had a large amount of observations which gave so much of science outcome ultimately. I'm not going into each of these instruments because for people like you, scientists, science enthusiasts, you can go into our Isro site and understand about those instruments and what each of the instruments did, etc. So I don't want to spend your time, so I only point you to the website of Isro where information related to Chandrayaan 1 is given in terms of instruments and how complex is instrument development, sensor development, building it to understand physical processes through electronic measurements. I think this is something each of you scientists should be encouraged to work on for the future. I'll only tell you this Chandrayaan 1 was a very unique experiment because when we did Chandrayaan 1, there was no LVM-3 rocket. The GSLV Mark 3 was not there. The only rocket we had safely to put a satellite around moon was only PSLV. And when we had only PSLV and we had to go to moon, a decision was taken that we must go to moon. Then the question of how to go to moon in a very frugal way, how to do it in a very unique way came up. And that is where the trajectory design, the design which we are all of us are knowing about Indian approach to go to moon came up. And that is continuing even after Chandrayaan 1 to Chandrayaan 2 and Chandrayaan 3, that we put the satellite only in an Earth orbit and progressively use the propulsion in the satellite to raise orbit slowly and finally make a translunar injection captured on the moon, then bring back the orbit smaller to be in the orbit of the moon. I think this approach gave us such an advantage that with a lesser payload capability, lesser cost, we could actually go to moon. And this is a very unique and nobody has done like this. Everybody wanted to go to moon straight in 4 or 5 days. We went to moon in 42 days. Is there any problem going to moon in 42 days? I don't think there is a problem. Unless there is an urgency to bring back somebody. So we decided that for a mission like this, it's the cost effectiveness and the frugality of engineering is more important, and we were able to do this using the available capability and available technology. That's the whole beauty of it. And you can see one of the picture, which is the map of the water presence on the moon, which is mapped by the payloads, which are payload instruments which were there on board Chandrayaan 1. And you know when it happened, this whole of this launch? Year? It's just a 1,380 kilogram satellite. It's a small satellite. It went up to moon and did the instruments in 2008-9 time. And Chandrayaan-1 outcome is the very important outcome in terms of the moon mineralogy, water presence, and various other mapping that happened across the moon. I think this was been a very unique thing. There are a lot of publications that came out of the science of the moon. Prakash is here. I think some of my colleagues are giving talks in other centers. I think they will be speaking about it or discussing about it. Chandrayaan-2 was a design which went into next step of Chandrayaan-1, where we wanted to have a landing on the moon. So the concept of a two craft, like an orbiter and a lander and a rover concept came out. And we have a new rocket by that time. The new rocket was LVM-3, which I was fortunate to be the project director, and being the first launch was successful. Later we made it operational. And this was the first operational launch of the mission after its development. And we took a decision that we will fly Chandrayaan-2 in the very first operational mission of the rocket. A great risk at that time, but then it actually paid off very well. We were able to put the satellite in the Earth orbit very safely, move it from Earth to Moon, and attempt the final landing. Of course, in the final landing time, we had some issues. But Chandrayaan-2 gave us such a beautiful images of Moon. And we had one of the best camera on board the Chandrayaan-2. We call it OHRC, high resolution camera, which gave almost 0.3 or less than 0.3 meter resolution. And today we have the very good images, both in terms of the entire moon surface is fully mapped by this camera today. The Chandrayaan-2 craft orbiter is still working, and it actually helped Chandrayaan-3 succeed, and this was a communication gateway for us. So it helped us in Chandrayaan-3 as well. But in Chandrayaan-2, you know, that landing process, of course, all of us were very disappointed. I was also there in the control room on that day, like the Chandrayaan-3 happening. And we were also all disappointed that in the final phase, we couldn't bring back the lander at the required velocity to have a soft touchdown. It actually went and crashed on the surface. Primarily due to various errors. As I said earlier, in every launcher rocket, errors can happen, and your ability to foresee the error and make corrections are actually very limited. It all depends on the simulation that you do in the ground. You know, before Chandrayaan-2, we never had any flight around moon to make a landing. So all the simulations that we did were on Earth. You know, what is the difference between Earth and moon in terms of the dynamics? One is, of course, gravity. You know, gravity is smaller there, almost 1/6, you know, it's almost 1/6, and there is no atmosphere. And more importantly, the gravity is not very neat gravity like Earth. No, it's a non-uniform gravity field. You have the symmetry of the moon in terms of gravity distribution or mass distribution is such a way that its orbit will never be circular, exactly. It's actually very wavy. And there are a lot of complexities of this aspect. Even atmosphere not being there creates a big problem for you. Because atmosphere is there, that your aircrafts are landing. Assume that your atmosphere is not there. How will you be flying in an aircraft? Can you ever thought about it? It's not easy without a helicopter. A helicopter and aircraft to fly without atmosphere. So landing is much better when there is atmosphere, because you can use the drag, the lift, and various other forces to control the landing process. But when nothing is there, the only way to land is by fuel, propulsion, the engine, and its control of that engine and the dynamics. So it creates a big problem. And we could never test it in the ground at the required gravity field. So everything is dependent on the simulation, the computer simulation, and limited tests that we could do. And this led some understanding, some errors in the software, some deficiency in the overall algorithms. So this all were identified. There were not one error, there were multiple errors. And all of this could be identified, and we could correct it for the Chandrayaan-3 mission. And the images that we got, fantastic images. I think I have just put only 1 or 2 slides here. It shows the craters on the moon to a detail so beautiful. And also we had radar images of the land location, where radar can actually penetrate deeper into the surface and understand craters present even if it's not visible with the naked eye or optical images. So those radars found out that hidden craters and hidden areas in the moon. I think all of these are very unique data sets that is being shared globally today. And Chandrayaan-2 also created beautiful, see one of the crater image you can see, it's called Sarabai crater, I believe it is. And We have other mapping of minerals and solar thermal distribution, exosphere composition, and so many outcomes that came out of Chandrayaan 2, which is very scientific outcome. But when we came to Chandrayaan 3, we wanted to make sure all the errors and problems in Chandrayaan 2 are resolved. But you know that in 2019 we had Chandrayaan 2 launch and landing, but the Chandrayaan 3 happened in 2023 only, almost 4 years. And it took that much of time to correct the problem and bring back the Chandrayaan program back on track. This is a problem with every failure. Once you encounter a failure, then it goes through serious debates and discussions, the organization, correction processes, and ensuring that the money that you spend on this are not wasted. Just you cannot try luck again. You must be very sure next time when you do this. So this process, almost 1 year we try to understand what went wrong. Next 2 years we did all the corrections and made the new set of hardware. And last final year we did a lot of simulations in the computer to make sure that the whole mission is rugged enough in case of parameter perturbations. Parameter perturbation is a very important topic, that when you design a system for nominal condition, you should also work for off-nominal condition. Some of you know statistics a little bit. You know what is a processes and distribution, sigma, standard deviation, 6 sigma, 3 sigma, all of you have heard about, I think. And how you generally say things will work up to 3 sigma, 3 times the standard deviation. But here we have tried up to 6 sigma, 9 sigma, and then see whether it will still work when parameters like the initial conditions changes, the performance indices changes, still you should go and land. Sensor degradation, uncertainty in measurements, and all this becomes a very important part of this mathematical simulation. I don't know whether Madhurav is going to speak about it in your presentation. Of course, the mission Chandrayaan 3 we had launched on 14th of July 2023 using the LVM-3M4 mission. It went to the Earth orbit. Then progressively we raised to a orbit which is enough for translunar injection. And translunar injection happened and we had the capture on the moon. And in the moon we had 5 lunar burns to bring it back to an orbit of 100 kilometers. So all this happened at the sequence. I just don't want to go through the dates. But for doing this, there were many constraints because you need to see the orbit. You need to have a ground station to see moon all the time because moon is visible to you. But when the moon set in the evening, there are ground stations on Earth. India cannot see that. Then you need some other nations' ground stations to connect you. So we had tie-up with the European ground stations, JPL NASA ground stations, one in Australia, and all of them were networked in such a manner that we have continuous visibility of this craft wherever it goes. Because it will go only around Earth, but still if we are not visible from Earth. And this support was so crucial for us. I think all of them came to support us and help us to make this mission succeed. So thanks to them. And it's also important for this contribution, yes. And this is the Chandrayaan 3 craft, where we made major changes from Chandrayaan 2 to 3. The first and foremost change was that the lander, the Vikram lander, is now made much more rugged, stronger. What way stronger? We put more fuel. We made a new propellant tank to increase the fuel quantity so it can handle more disturbances. It made its legs stronger so that it can impact the land with a higher velocity, typically 1 meter per second higher than last time. We put solar panels. Only one face it had solar panel. If it didn't face the sun, suppose it lands like this, then the mission is gone. So we decided that we will have solar panels on other faces in case something goes wrong. Still it will generate some amount of power. We made redundancies in the system. We made new sensors like the laser Doppler velocimeter, which will measure the speed of the craft related to the surface of moon using lasers. Then we inducted new batteries, new power systems, and new sensors, new cameras, etc. to help the decision making, which using those cameras you had the beautiful image of landing, and the rover could take the video of the lander, and reverse way, lander could take the video of the rover. All of this are happening because of the improvements in this craft. But the orbiter was made lesser in capacity, where there are no instruments, no experiments on board, because the orbiter is already there. So we made just a propulsion module to do the function of moving it up to the moon. And the rest of the systems were the same. The experiments, the 5 of the experiments, is the same. So this was essentially the lander, which is called the Vikram lander, and designed only to work for 14 days. You know why 14 days? The moon day is 1 week. of Earth week, Earth 14 days, and after that there is a night for another 14 days, then again sunrise occurs. So, because of this, until the sun lasts for 14 days, we can do the experiment. After that, the temperature of the moon surface will go well below 200 degrees, below 0 degree. So, none of the electronics will work, the battery will drain. And since you do not have any other alternate power source, we cannot work further. So, whole thing was designed to work, land on the first day or near to the beginning of the day, and then experiments to continue for next 12 days, 14 days, and then finish off everything and allow the whole lander to sleep for the next 1 week or 2 weeks, and then see whether it will wake up after that. So that's how it was designed. And I mind you that we were able to achieve this landing spot very precisely. Where we wanted to land, we achieved the landing within 300 meters. That was the precision. Now the Pragyan rover is also just the same as what we did last time in Chandrayaan 2 with 2 of its payload. I will quickly tell you the experiments that we did on board. But the landing process, I think you probably would have watched online and then seen how it landed. There was good animation from computer, but reality animation were one and the same this time. So there was no issue. So the landing happened as planned in the nominal manner. Though we had contingencies, so many contingency options in case something doesn't happen, some sensors fail, but everything worked as expected. And the touchdown speed was actually well below the nominal expected touchdown speed. So we had a very healthy spacecraft with everything working, and all the experiments could be done without any problem. So this part, I think Madhuraj will be speaking further, so I won't spend time on it. Another important part was the rover path planning. After this landing, we were trying to bring out the rover out, so we had to open the path for which to come out, and then all the mechanisms worked, the rover came out, but we had some tense moments there. It was not coming out that easily that we thought. We had to do some commanding, we had to do certain modification, etc. to bring it out. But after it came out, very well it moved around, almost 100 meters on the moon. We had a beautiful path planning and almost fell into a ditch. Luckily we saved, understood from the camera that it is going towards a crevice, no, rather a pit or whatever. And then it negotiated and then came back to the same location safely, and rocks and other obstructions were understood by the camera and could navigate and do various scientific instruments on the moon. And there were 6 instruments essentially to understand the moon. 3 of them were on the lander and 2 of them were on the rover, and the shape was on the orbiter, which was still in the orbit. So what exactly we were trying to find out in the moon mission? 1, we were trying to find out the lunar regolith thermophysical characteristics. So there was an experiment called Chaste, which did some drilling and did some measurements of the regolith in terms of its thermal conductivity and other behavior. And there was a payload called Rembha, which looked at the very low altitude ionic characteristics, the presence of the electrons and the charged particles in that zone. And the third instrument was ILSA, which is nothing but a seismic instrument looking at measuring the accelerations or vibrations, shocks, or rather I would say seismic activities happening in the moon due to various activities, even physical movements or even seismic activity. And there were 2 other instruments were APEX and LIPS, which were essentially the moon mineralogy finding using spectroscopy. One was using an alpha particle exciting those materials, and the second was using a laser ablation and then doing a spectroscopy on it to find out the elemental parts. So both these instruments were on this very small rover, and it worked beautifully well. And the last instrument was called SHAPE, which actually looks at Earth from the orbit of moon and try to capture some signatures of a living planet. Suppose we look at a planet which is far away called exosolar planets, what type of signatures that you are going to get indicating the presence of living organisms in such a planet? And this was a question, and the measurement was in certain spectral band which will give certain signatures for us to decide future. So all these instruments worked beautifully, and we had beautiful confirmation of all instruments deploying. Rembha well called for deploying a boom. ILSA had to drop it from the bottom of the Chandrayaan 3 on the surface using a crane type of arrangement. Everything worked, and we had a lot of data collected, and our scientists are working on this data for the future. Let me also go to another important mission called the Mars Orbiter mission. I think all of you are familiar with this Mars mission. And this was again one of the first mission in any country achieved success in its very first attempt. I think this is very unique for India. And Mars orbital mission was achieved using again PSLV rocket with a very low payload capability. And Mars orbital mission produced so much of scientific outcome in various ways, including, I will skip and then go to a beautiful image of Mars. You can see a three-dimensional image of Mars, which came out of the Mars orbital mission imagery, which is one of the beautiful things that Mars is a very unique planet. It's almost like Earth, having almost 24 hours for a day, gravity very near to Earth's gravity, and temperatures not suitable for us, atmosphere very thin. So the people say that it is a planet where human being can one day go terraform it and convert it to a habitable planet and live there. Of course, possible, maybe. Our Elon Musk is behind that. But then you also should understand that Earth can also become a Mars if you do not understand the whole process of changes that will happen in planets over a period of time. People say there were water flowing on the Mars, the atmosphere was thick, all this were there once, and why it vanished? It's a very important question for us who lives on Earth. Not for you today, not for your children, but maybe 100 generations later this question will become relevant for each one of us. So science of understanding of planetary evolution is so important. That's why Mars is so important for us to study in the future. I think not much talked about satellite is called AstroSat. I think how many of you have heard about AstroSat? Very less, I believe. I think AstroSat is very important satellite which is equivalent to, I will say it's a Hubble Space Telescope of India. Though it is looking much smaller, very low in cost, but today AstroSat also produces an equivalent type of outcome as much as produced by other astronomical satellites. The uniqueness of AstroSat is still working. Are you aware that it is still working and so much of science is being done? It's not, many people don't even know about it. It has a large area X-ray, proportional counter, soft X-ray telescope, and also scanning sky monitor and ultraviolet. So we have observation various spectra for a celestial event. For example, you have a look at black hole, star explosion, supernova, or deep into the universe. And many of these observations are in certain bands. But here we have an AstroSat which is very unique in terms of the spectral distribution observation. So this gives you very important correlatable information using various frequencies. And some of the important findings for AstroSat includes identification of new solar exploration, identification of new galaxies, black holes. I think many of the astrophysicists of our generation are making use of AstroSat data. Aditya L1 mission, I think many of you would have heard about it because it happened this year, and we were sending a satellite to study the sun, right? Why sun is important for you? Sun is anyway there, shining up beautifully, every day it rises, every evening it sets, and you don't see any change in sun, no, when you look at it. But the reality is that the sun is a very dynamic star. It has a lot of activities which influence us, especially the solar coronal emission and its impact on space weather, the climate and weather, etc. So, study of the sun has been a very continuous activity. There are many satellites launched to study sun. The latest being, anybody can tell, not other than ours. A satellite which is launched to study sun, other than Isro's Aditya L1, Parker Solar Probe. Somebody said? Yeah. So there are very satellites which are recently sent to study sun, and this continues to be a global interest in understanding sun. So Aditya L1 is again a unique satellite which is made using multiple instruments. We have 7 instruments on board Aditya L1 to study. One, look at the solar corona by closing the disk of the sun and look at the corona, which is almost 2-3 diameters bigger than the sun's diameter. Then look at the solar coronal mass ejection. Look at the X-ray characteristic using soft X-ray and hard X-ray. Then again look at the particle emissions. Then also look at the magnetic effect of such emissions in the vicinity of the space between sun and earth. So all these instruments will look at a correlatable information connected with the solar mass ejection. Now, corona is a huge activity. Tons and tons, I don't know whether ton is a right mass to be describing CME. Huge amount of mass is ejected in terms of particles, which includes hydrogen, helium, iron, and very higher elements. Everything gets ejected into space, and this travels because of the magnetic effects towards Earth, and it creates a lot of effects on the outer space around Earth. So understanding this is so important. I think that's why the launch of Aditya L1 happened, and we are going to put in a very unique place called Lagrangian point L1. Reaching up to this point and then keeping it is another interesting story. So I don't know whether you are speaking about it. No, I think Madharaj is not speaking about it. So he says, so we will be launching. We have launched it into an Earth orbit. Then from there it has been moved out of the gravity field of Earth and it's going towards Lagrangian point L1, which is a neutral point between Sun and Earth, where the gravities of both these bodies almost neutralize each other. But it's not a point, it's a region, because there are other bodies, multiple bodies affecting this whole process. So we have to achieve that orbit, which is called a halo orbit, in few lakhs of kilometers in diameter. So we are going to study these processes in great detail. And we are building new satellite called XPOSat. This is just getting ready for launch, looking at X-ray polarimetry of black holes and other objects. So this launch is going to happen on 1st of January. So all of you can watch. And the next launch is going to happen is SpaceX, trying to understand how to dock satellites in orbit. So which is important for human space flight in the future. So this is X-ray polarimeter satellite, where there are important two payloads called POLIX and EXPECT. Look at the polarimetry of the radiation happening from black holes to understand its accretion of the material. See, you know, black holes take material from other stars, and when this happens, there are some X-ray emissions, and you can look at the polarimetry of this and understand the quantification of this is possible in such experiments. So this is the basis on which such instruments are built. We are also working on various science missions in the future called Disha, Venus Orbiter, Mars Lander. I think all these are still in planning. Looking at the science aspect, the design aspect, etc., still not got government approval. Of course, we will be seeking government approval for all these missions in the future. We are working on landing on the moon along with Japan. We call it UPEX mission, where the lander will be provided by India, the rover from Japan, and launch will happen in Japanese rocket. And we are also looking at future astronomy missions, creating another satellite for exoworlds. Look at the exosolar planets. Do you know what is exosolar planet? Exosolar planets are the planets which are planets of other stars, not the Earth, not the Sun. So every star has got planetary system, and many of them are similar in nature to Earth. Some of them may have possibility of life existing. So it's a very interesting topic. So that's what we want to study and look at the atmosphere of such planets, because these planets are not visible because they have no light emission. So we have to do separate techniques to understand the atmosphere using the light passing through the thin atmosphere, and its spectroscopy of that will give us some idea about the nature of the atmosphere. So this is a mission. And we would like to work on a series of science missions in the future. And as I already mentioned, so I will not explain this. But the most important part is in all these science missions, we are collaborating with other nations. We are working with Japan, we are working with Europe, we are working with America. Are you aware of a satellite which is being built by India and NASA today? The satellite is in Bangalore today, called NASA Isro Synthetic Aperture Radar, NISA satellite. It's one of the costliest satellites ever built for the Earth observation. Looking at Earth in two radar bands, L band and S band. Look at the tectonics, the ice, the water, the vegetation, and various other aspects of Earth can be measured using global observations, which are very fast compared to many other satellites. So we collaborate with France, and many other nations on building future satellites. While we build satellites, we also do a lot of science experiments in the ground. And across Isro centers and other collaborating laboratories, we have huge observational capability of radars, instruments on the ground, correlatable radar observations, balloon experiments, etc., etc. So our scientists work on various aspects of observation, including climate modeling, weather modeling, and helping other agencies in India to help us in terms of parameters that can be observed using space as well as ground-based observations. Some of you may know about the essential climate variables that decides the climate change. So how many of you are following the COP28 meeting that's happening? I don't know. Huh? Some of you are following. So the narratives on weather and how the greenhouse emissions cause the annual temperature rise of the globe, and how you can control them, how to minimize the greenhouse emissions. All these questions are very important topics. I think all of you should read it. Very important. It's not nothing space technology. It's a very simple technology to understand how greenhouse gas emissions control our future. So we study atmosphere using so many instruments like the balloons on days. We conduct ascents of balloons and measure various characteristics, and we use it on a regular basis to help model the atmosphere properly for various applications. So it's a very major activity. Along with atomic energy also has certain capacity in this, so we work with them and various other laboratories in India. Aerosols. You know aerosols, heard about them? Some of the chemicals which actually cause a lot of issues in the atmosphere, nucleation of various activities and how it controls the pollution and other radiation effects and suppression of the radiation. All these are important and we need to measure aerosol emissions and characterize them to control it for the future. So this is again space and ground-based observations we carry out. We study the clouds and how clouds impact our radiation, and we have even sent satellites as well as we do ground-based radar observations continuously to understand radiative impact of clouds on Earth's weather. We also conduct experiments on rocket stages. We have an upper stage of rocket which we use instruments. Suppose some of you in colleges have an interest to build an instrument and we want to launch it. I think you should send a mail to me and I will give an opportunity for you to build the first instrument to launch on PSLV. Are you ready? Some of you are ready to do this? So I would like to invite you, don't have to make a satellite. You can design a small instrument, a small electronic card. We will put it in the rocket and then send it up and then do the experiment for your college. We are happy to do that using very low cost systems. Sometimes it will be free also for launch. So I will hope that from Goa and universities here, some of such experiments will come up in the future. And on 1st of January, when we are launching PSLV, there is such a platform. There are 10 experiments from various startups, companies, institutions, colleges. We are hosting on PSLV. So I welcome you to do this in the coming days to create enthusiasm and energy in this sector. We also work on robotics hugely, on space robotics as well as ground-based robotics. So this is another interesting area. We have a recently announced Isro robotic challenge. Have you seen our website? Please go and see our website. There is an announcement of Isro robotic challenge. And anybody has an idea of how to design the future robot to go in a Mars or a moon, your idea will be taken by Isro and possibly some of your ideas will be the one which will fly in the future. So we welcome all of you to look at our website and offer your ideas as a robotic challenge competition. We also work on human spaceflight, as I mentioned, and we have a great goal, a vision given by Honorable Prime Minister recently. He said that we must build a space station by 2035. We must also land on the moon by 2040. It's a great vision that our Honorable Prime Minister has given, and we are going to work on this. And for that, so many new things are required. I will only want to speak about it and then close my talk. Finally, we have to have a human-rated rocket, which is shown there. The Chandrayaan 3 we launched will not be the last of the Chandrayaan series. We will have many Chandrayaan launches to understand moon much better, because if you have to go and land there, you should understand moon much better than others. So we will be having sample returns or unmanned launches or robotic launches and robotic activities on space without human going there, and then finally make a human landing. We should develop newer rockets with higher capacity, so we can't take a person to moon in 42 days. When you are unmanned, you can take long duration, but if man is there or a woman is there in the satellite, then it must reach there in 4 or 5 days of time. So we need a much more powerful rockets. And finally, we must have a space station to conduct future experiments in science and technology. So these are our goals, and all these goals are going to be happening now because a clear vision by the government is there in front of us in Department of Space and Isro, and we are going to work on it. I think all of us will vanish in few years of time. I think all you young people will be the one who will do all of this work. So I go everywhere and tell them, unless you are there to do it, none of these dreams are going to happen. I think it is a dream and vision that is given by the government, and it is your responsibility to make it happen. So I look forward for such a challenge from you. You means you don't have to be in Isro today. I think to do all of this, as I told you, a robotic challenge we announced. The future robots possibly will be designed by a company or a startup or an individual who have a flair to do this. So you can all be part of this activity. And there are a lot of innovation and challenges we are offering. In fact, we have offered almost 100 new technology developments to Indian industry for space sector. Many technology we announced, and a lot of offers have come from Indian industries and startups to work in space sector, and you can be part of the whole journey. Today, almost 200 startups and companies are working in the space sector in various areas. At least 3 companies in rocket building, another 5 to 10 companies in satellite building, and hundreds of companies in application development and component development. I think it's a really wonderful thing to happen after the space sector has opened up. It's a huge opportunity for all youngsters to work in so many technology domains. So I like to conclude my talk saying that the Vision 2047 is for India to become a leading spacefaring nation, having a manufacturing hub for space activities, a startup ecosystem, an innovation place, a low-cost design and production area for all of us, for new generations and industries to come forward to create a vibrant space ecosystem. The whole of exploration activities are focused on creating this capability. Unless the scale of our space activities increase, none of these dreams are going to happen. And it will happen only when, with your participation, young people taking more interest, studying more on science and technology, and contributing in various ways. Whether you are in academics, whether you are in industry, whether you are in Isro, all of you will be in a position to contribute to this greater vision. So with this, let me conclude and thank you so much for this opportunity.